prediction is the problem of predicting a unobserved outcome y from an observed variable w1, and it could be w2, w3, or w4, but we'll just focus on the simple case here of just a single predictor. In this video, we're going to dig into the details of how we choose a predictive model, how we estimate that model, and how we apply it to generate predictions. We break this down into 3 steps, and we'll start with step 2 and fill in step 1 later. So step 2 is all about finding a prediction strategy. So here our prediction strategy is represented by this arrow. And how do we operationalize this arrow? So we think of this arrow as representing a function g that takes w1 as its argument. So when we plug in w1 into this g function, we get a predicted value. And hopefully this predicted value will be close to the unobserved y that we want to predict. We'll continue using our old example where y is your wage at age 30 and w1 is your college GPA. Now, presumably, this is you're interested in this prediction problem because the wage is not yet observed. However, to learn what a good function g is, we need data where we observe both the predictor and the predicted outcome. So let's assume that we have such a sample, and in practice we could use, for example, previous cohorts of students who are already 30 or older so that we observe their wage. So we assume we have a sample where we have data on the outcome that we want to predict. We have data on the predictor. And such a sample is called a training sample. Using the training data to find a good function g is called training the model. Now that we have found our g function, we want to apply it to new data, and this is step 3. In step 3, we are making predictions. So suppose that we have new data on a new student for who we observe w1. And by new data, I mean that this w1 is not contained in the original training sample. Such new data is called out of sample data. So this is an out of sample observation. Right now we're only observing the predictor, but at some point there is an outcome that corresponds to that predictor, and so we don't observe it yet, so I gray it out, but it will be revealed in the future. So before this is revealed, we want to predict it, and to do that we'll simply plug in this w1 into our function g, and this will be our prediction, and we hope that it will be close to the y that will be revealed in the future. Let's talk about what makes a good function g. Good function g is a function that performs well on out of sample observations. And how do we measure performance? We measure performance using a concept called the expected prediction error. What is the expected prediction error? Let's take this apart word by word, and we'll start with expected. So expected has something to do with expectation, so there's some randomness. And where does the randomness come from? Well, we're talking about the randomness in the out-of-sample prediction. So we're taking the view that we don't know yet who we will be predicting for, and so we just predict for a random individual and hope that this works well in expectation. So let's see at our out of sample observation. This is the randomness we're talking about. Next up is the word prediction. So our prediction is this g function evaluated on the out-of-sample observation. Loosely speaking, we can think of a prediction as a guess of the unobserved outcome. Now let's move on to the last word, error. So when we make a prediction, we can be a little off. So this happens, right, if our prediction is not exactly equal to y. So the difference between those two quantities is called a prediction error. Our prediction error is the difference between the outcome that we're trying to predict and our prediction. So let's square this so that if we are exactly spot on, this will be 0, then the square is also 0. If we are slightly off in like one direction or the other, it will be a small positive number, and if we are off by a lot, then this will be a large positive number. So since y out of sample and w1 out of sample are random variables, this here is describing the prediction error for all possible realizations. If we want to break this down to a single number, we can just take the expectation. And this gives us the expected prediction error. Let's abbreviate this by EPE. Now that we have agreed on how to measure prediction error, we can start thinking about how we should choose our function g. So we're wondering, what is the best prediction? And we've already talked about the problem of minimizing this kind of least squares criterion, and we know that if we want to minimize this criterion, then we should be choosing the conditional expectation of y given w1. If we want to use this kind of g function, then we have to take into account that the conditional expectation is also, of course, not known, and we would have to estimate it in this step 2. But this might actually not be a good idea, and let's think about why. What does this g function look like? Well, it is potentially a very complex function. For example, it may look kind of like this. We don't know. But it could potentially have such a very highly nonlinear shape. The problem with such highly nonlinear functions is that they are difficult to estimate. So we may instead just try not to use the actual g function, but a approximation of the g function. So we could go like, hey, instead of the conditional expectation, we're using an approximation of the conditional expectation that is linear. So something like this. It has an intercept and a slope coefficient that multiplies the w1. And if we use such a linear approximation, then we wouldn't be replicating this complex shape. Instead, we would find something that looks like this. So this might be too inaccurate. So we may actually want to replicate these bumps. Maybe replicating these small up and down movements is not necessary. But to replicate these, the shape like this, we would have to have nonlinear terms. We may, for example, then want to add a quadratic term, maybe a cubic term, and potentially we could have something like a sine function and so on. So we may want to use a number of transformation of our predictor and then use this kind of linear form in the transformations to approximate the conditional expectation. And then actually we may be able to get something that approximates the conditional expectation fairly well, maybe something like this. So let's be agnostic about what transformations we use, and we just call like the first transformation that we use, we call that x1, and then the next ones will be x2 and x3, and we could add more if we wish to do that. So such transformations are called features. And finding such features is the missing step 1. it is called feature extraction. So we find transformations x1 up to xk. And then in the subsequent steps, we actually don't have to think about w. Instead, we're thinking about x's. And now we're back in the setting with a y and lots of x's. But we have some framework to think about where they come from. Now, once we have decided on the features, we know the functional form we want here. We want a linear form in the features. And now what's left to do is find these coefficients. And obviously we want to choose the best coefficients that give the best approximation to the conditional expectation here. And we already know that the best linear approximation of this is the best linear prediction. The best linear prediction of y given x1 through x3 in this example with 3 features. And as we did before, we'll denote the corresponding coefficients by b0 star star, b1 star star, b2 star star, and b3 star star. These coefficients are unknown population parameters, but we know that they can be estimated by using OLS. If we compute the OLS coefficients based on, if we computed the OLS coefficients from the training sample, those would estimate these coefficients that we're looking after. To be sure that the OLS estimator gives us unbiased and consistent estimates of these coefficients, we just require that the training sample is a random sample. No other assumptions are required. And this is different from causal inference. In causal inference, we had a functional form assumption, and if we assumed an incorrect functional form, then causal inference didn't work. This is not the case here. So here we're working explicitly with an approximation, and if we choose a different features, we will maybe not be able to approximate the conditional expectation as well as we would want, but it's not like that our method is breaking down completely. So no functional form assumption, so our assumed functional form can be wrong. Assumed functional form allowed to be incorrect. Also, we don't need any kind of exogeneity assumption. So now let's go back to our 3 steps. We had step 1, feature extraction, and now we understand that we are looking for features to approximate the conditional expectation. Next step is training the model. Now, once we have our features, it's just running a linear regression on the training sample. And then finally, we look at the out-of-sample predicted values on new data. That wraps up our first overview of prediction.